Imagine you had a magic box that could create anything you wanted. You can ask them for an apple, and an apple will appear. Ask for a pencil, and a pencil will appear. Or even ask for a unicorn, and a unicorn will appear. The strangest thing is that the box doesn't decide what to create until you open it and look inside. Before you look, he can create anything you want. Only after opening the box does it choose one thing and become that apple, pencil, or unicorn. All of these possibilities exist simultaneously in the box. This is similar to how particles act in quantum mechanics before they are observed. They have been observed to exist in a state where they can be many things at once, and when they are observed, they collapse into one state. One interpretation of this phenomenon is the Copenhagen interpretation, which suggests that it is the observation of a particle that causes it to adopt a particular state. This process is known as wave function collapse. The act of measurement affects the particle in such a way that it cannot remain in superposition, but instead assumes one specific state. In our story, opening a box and looking inside is like observing a particle that is one thing. The ancient Greeks believed that the basic elements could be air, fire, or water. It was a revolutionary idea at the time, attempting to explain the diversity of nature using a limited set of basic substances. 100 years ago, physicists were convinced that they were atoms. Experiments conducted by Max Planck, Albert Einstein, Niels Bohr, and others showed that atoms themselves are composed of even smaller particles that exhibit strange behaviors inexplicable by classical physics. Modern physics tells us that the building blocks of the universe are subatomic particles, such as electrons, quarks, and neutrinos. These particles are believed to be the fundamental components of matter, and all the matter we see around us is made up of various combinations of these particles. However, the story does not end there. It doesn't end there. Quantum theory reveals that the fundamental building blocks of the cosmos extend beyond particles themselves, extending to the very fabric of space and time. In this view, the universe does not consist merely of particles moving through space, but is rather a dynamic interplay of fields and forces in the structure of space-time. These fields described by quantum field theory are the true essence of what constitutes reality, and particles appear as excitations of these fundamental fields. Today we believe that the deepest layer of reality consists of elementary particles governed by quantum theory. Quantum theory. This invisible, tiny reality is the source of everything we see and experience. It is a world full of wonders that can often seem strange. Let's start with what we know. Visible matter consists of atoms that have protons and neutrons at their centers. However, these protons and neutrons are not the smallest particles according to the standard model of particle physics, which explains reality at the smallest scales. There are even smaller particles. Surprisingly, everything in the universe can be reduced to atoms. An atom is the smallest unit of matter that retains the characteristics and properties of the larger visible world, including physical and chemical properties. An atom is essentially a quantum entity with its own energy levels, properties, and conservation laws. It interacts in many ways with all four known fundamental forces. All of physics can be seen in a single atom. This is what atoms can tell us about the universe. There are about 90 naturally occurring elements on Earth that were created as a result of cosmic processes. Each element has an atom with a nucleus composed of protons and possibly neutrons, surrounded by electrons equal to the number of protons. Each element has unique properties such as hardness, color, melting and boiling points, density, conductivity, electronegativity, ionization energy, and many others. What is unusual about atoms is that each one has only one property that determines what kind of atom it is, and therefore what properties it has. Number of protons in the nucleus. In everyday life, there are certain rules that we take for granted. For example, cause and effect. Something happens and causes different events depending on what happens at the beginning. Different causes lead to different effects. However, in quantum physics, the standard rules are fundamentally different. Even the starting point cannot be defined with arbitrary accuracy, because some properties of the system are subject to uncertainty. There is no predictable deterministic way to describe the evolution of a quantum system over time. You can only calculate a set of probabilities. If you measure an observation or interaction precisely enough, you will see one result. However, the very act of measuring an observation or interaction changes the state of the system. This behavior has been a subject of debate for almost a century. The solution may be disturbing, not to interpret it at all, which is as mysterious as it sounds. Interpretations may be what prevents us from truly understanding quantum reality. Quantum theory is an extremely effective description of the microscopic world of atoms and their components. But what is disturbing is that it also reveals a deeply counterintuitive reality in which, for example, a particle can exist in a superposition of states in which it can do two or more things simultaneously. In 1935, Erwin Schrödinger developed his famous thought experiment to illustrate the consequences of quantum theory. He imagined a cat locked in a box with a vial of poison. The decay of a radioactive atom could trigger a hammer to shatter the vial and, as a result, kill the cat. If the atom were in a superposition of decay and non-decay, the cat would be both dead and alive. The only way to find out would be to open the box. This thought experiment brought quantum strangeness from the micro world into the everyday world, forcing scientists to grapple with it. Physicists call these macroscopic superpositions involving many atoms or other quantum entities Schrodinger's cat states. Over the past decade, these cats have helped scientists explore the transition between the quantum and classical worlds. They also began to explain why we can't see everyday objects in two states at once, and whether we will ever be able to do so. The idea that a theoretical quantum animal could be both alive and dead is a classic example of quantum weirdness. Questions such as how or why quantum physics works or what mathematical objects in quantum theory represent, if they represent anything at all. They have as many answers as we care to give them, but those answers probably say more about ourselves, our prejudices, biases, and assumptions about the universe than they do about the reality of the universe. There are very few things that we can actually observe in nature, such as particle properties, position, momentum, scattering amplitudes, individual quantum states. The question about the fundamental nature of reality assumes that it obeys rules that are consistent with our intuition, but the opposite may be true. Our perception of reality is limited by our senses and capabilities, and the true rules that govern the universe may be more alien to us than we can imagine. We are talking about particles that occupy points in space, but in reality, they are energetic impulses or excitations in fundamental quantum fields. For example, a photon is an excitation of an electromagnetic field. These fields permeate the entire universe. This means that there are always some residual particles everywhere, so-called virtual particles, which appear briefly and disappear even when there is not enough energy to create a real particle. Fields are considered more fundamental because without them, mathematics does not work. However, the quantum nature of the field means that it cannot be observed directly. Every observation requires energy that forces the field to produce a particle. That's why we often talk about particles, because they are what we can observe. Almost every particle has a corresponding antiparticle with the same mass, but opposite charge. Antimatter is rare in the visible universe and is mainly created in particle collisions. The universe is made up overwhelmingly of matter, and no one knows why. The quantum world operates according to principles that defy common sense. A particle can behave like a wave under certain conditions, and even the concept of a particle becomes uncertain upon closer examination. Trying to determine the position of a particle obscures its momentum, and recording its momentum obscures its position. This is the Heisenberg uncertainty principle, suggesting that these properties themselves are inherently vague. The most surprising aspect of quantum physics is the minimal number of properties needed to define a particle. Mass, charge, and angular momentum or spin. Thanks to them, a mathematical equation can fully describe a particle in terms of its wave function, which predicts the probabilities of its behavior. This concept is closely related to wave-particle duality and superposition. Particles exist in a range of wave states until they are observed, at which point their wave function collapses and they assume a particular state. However, the question of who or what is needed to observe this collapse remains unanswered. Are detectors enough, or does human consciousness play a role? Quantum physicists have proposed various interpretations ranging from the necessity of human consciousness to the idea that the collapse of the wave function is illusory and all possible states exist simultaneously in multiple universes. Many worlds interpretation. There is no clear answer. What we know about the universe today, we learned by asking the right questions, that is, by creating physical systems and then making the necessary measurements and observations to determine what the universe was doing, despite what we might have previously intuitively imagined. The universe has shown us that the rules it follows are bizarre, but consistent. These principles are simply deeply and fundamentally different from anything we have ever seen. Reality, if it can be called that, is not an objective existence. Beyond what can be measured or observed in physics, our ultimate goal is to describe as accurately and fully as possible what can be observed and measured. By creating a theory in which quantum operators act on the quantum wave function, we can precisely calculate the probability distribution of possible outcomes. For most physicists, this is enough. However, assumptions can be added to these equations, and different interpretations of quantum mechanics can be obtained. Is the quantum wave function meaningless until we measure it? Do all possible outcomes occur, requiring an infinite number of parallel universes? Should we imagine reality as an infinite number of identically prepared systems, with a measurement selecting the one that represents our reality? Do particles always have real, unique positions, guided by deterministic pilot waves in a non-local, local way? There are different quantum interpretations based on different assumptions about properties. Despite the differences between them, no experiments can distinguish these interpretations from each other. Although some interpretations, such as those with local, real, deterministic hidden variables, can be ruled out. The frustrating thing is that all of these interpretations, and others, are experimentally indistinguishable from each other. We have been unable to design or conduct any experiment that would distinguish one of these interpretations from the other. Therefore, they are physically identical. The idea that there is a fundamental objective reality, independent of the observer, is an assumption without any evidence, based only on thousands of years of our intuition that tells us that this is how it should be. Science does not aim to confirm our prejudices, but seeks to discover the nature of reality, regardless of our prejudices. To understand quantum mechanics, we must abandon our prejudices and accept what the universe tells us. Entangled photons emitted from a source to separate observers show random outcomes but exhibit correlations. Whether these correlations are consistent with local realism depends on whether they are consistent with or violate Bell's inequality. Understanding the universe is not about revealing a true reality separate from the measurements and interactions of observers. Reality can be linked to measurement, observation, and interaction at a fundamental level. To better understand the universe, we need experimental tests that can distinguish interpretations. So far, only interpretations requiring local realism have been excluded. The choice between interpretations is a matter of aesthetics. Experimental measurements of polarization correlations are consistent with theoretical predictions from quantum mechanics, indicating that local real correlations between photons cannot explain the observed precision in science. We can determine what reality is, and then adapt our observations to our assumptions. Theories and models that predict observations with accuracy, predictive power, and minimal assumptions will survive. Physics doesn't care that reality seems mysterious and bizarre. The problem only arises when we demand more from the universe than reality offers. There is a strange and wonderful reality until we develop experiments that teach us more. It is better to accept reality as we can measure it than to impose additional structures based on our prejudices. Until we conduct this crucial experiment, we will be philosophizing superficially rather than relying on scientific intervention. Until then, we will remain in the dark. Quantum mechanics remains the most accurate and powerful theory of reality, predicting countless experiments and giving rise to numerous applications. However, physicists and philosophers remain divided on its interpretation. Many physicists, perhaps most, subscribe to the Copenhagen interpretation, which suggests that physicists should focus on calculations rather than trying to understand the deeper meaning of quantum mechanics. Philosopher Tim Maudlin criticizes this approach, pointing to several interpretations of quantum mechanics that offer detailed explanations of how the world works. However, other scientists examining these interpretations reinforce skepticism because they seem convoluted and improbable. They do not explore interpretations that present quantum mechanics as an information theory, which some find attractive. However, for others, these information-based interpretations seem even less plausible because they introduce consciousness into physics, undermining its objectivity. The debate about consciousness is equally controversial. Previously, there was a consensus that consciousness arose from neural processes, but empirical evidence to support these theories was lacking. As a result, there are now many theories, including integrated information theory and proposals, suggesting that consciousness is based on quantum effects, although evidence for the latter is sparse. The journey towards understanding quantum reality goes beyond the limitations of our basic perceptions. It is easy to be tempted by what nature reveals directly to our senses. Evidence gathered from our basic perceptions often gives us a hazy picture of the world we live in. Assessing existence without taking into account the insights of modern physics would be like fighting in the dark against an unknown opponent. By deepening our understanding of the true nature of physical reality, we profoundly change our perception of ourselves and our experience of the universe. Quantum physics is fascinating because it contradicts our everyday experiences. Matter can behave both as waves and as particles. The universe consists of indivisible quanta. We can only predict probabilities, not specific outcomes. And the universe operates non-locally, both in space and in time. Its effects are most visible on the smallest scales, making it one of the strangest discoveries about the universe. However, we often bring ourselves into the equation by introducing concepts such as observation, measurement, and interaction. By removing ourselves, we are left with the equations, results, and answers of the universe. Physics cannot explain why the universe works the way it does. It can only explain how it works. To understand the fundamental nature of reality, ask the universe questions about itself and listen to its answers. Everything we add is our own construct, not the universe's. We've covered a lot of ground in this video, and one of the key takeaways is that quantum mechanics, despite being the most accurate and powerful theory of reality, remains a mystery when it comes to its true meaning.